I'm Aditi Netwewala from University of Pittsburgh. Today my talk is on interplay between electron pairing and anomalous Hall effect in lanthanum aluminate strontium titanate nanostructures. Before starting, I would like to thank the Vannevar Bush faculty program for supporting this work. We work in the field of correlated nanoelectronics, which basically arises from two well-established fields. On one side, we have the correlated electron physics, which is mostly studied in bulk materials and shows interesting phenomena like superconductivity and magnetism. On the other side, we have the semiconductor nanoelectronics, which allows us to have single electron control, thereby studying the quantum properties of the system. Now, at the interface of the two are the complex oxide heterostructures, which combines the rich correlated electron physics with the capabilities of semiconducting systems. Now, we are particularly interested in the 2D electron system at the LaAlO3 interface, and for a variety of reasons, this system is very different from any semiconducting system. So, firstly, strontium titanate undergoes a cubic to tetragonal phase transition at 105 Kelvin, forming ferroelastic domains along the X, Y, and Z crystallographic directions. And these ferroelastic domains have been shown to play a significant role behind the transport properties at the interface, like the observance of enhanced conductivity along the domain walls. Another very interesting property, which was seen in 2D Hall bars etched at the LaAlO3 interface, was the observance of anomalous Hall effect. So the Hall resistance was found to be a nonlinear function of the total magnetic field, and there's a critical magnetic field at which there was an excess release of magnetization. This anomaly was attributed to the multiband nature of the 2D electron system. However, the multiband picture is not applicable in the small field regime. Another very interesting property of the LaAlO3 interface is the observance of electron pairing without superconductivity. So back in 2015, we showed that single electron transistors written at the LaAlO3 interface supports paired electron states far beyond the superconducting critical magnetic field of 0.2 Tesla. We later showed the same in electron waveguides written at the LaAlO3 interface. So if you notice, there is a very interesting aspect about the anomalous Hall effect and electron pairing without superconductivity, and that is that they occur in the same parameter regime. So this led us to think that can the non-linearity be related to the d-pairing of the electrons? And if so, what can be the common link between the two states? Can the ferroelastic domains in STO play a possible role behind it? So we wanted to conduct a study where we can study the pairing mechanism and the Hall properties simultaneously, and also have control over the domain properties of the system. So in our lab, we use the conductive AFM lithography procedure to write our nanostructures. So basically, we apply a positive voltage to the tip, which protonates the surface, attracting electrons to the interface, and the nanostructures can be as small as 2 nanometers. We can reverse the process by applying a negative voltage to the tip, and we use this technique to create our tunneling barriers. So using the conductive AFM lithography, we have written ballistic nanowires at the LaAlO3 interface. So here, if you notice, our main channel is separated from the source and drain by these highly transparent tunneling barriers, which allows us to tune their chemical potential with the help of a side gate. Now, if we plot the conductance as a function of the chemical potential and magnetic field, we can clearly see the Landauer quantization plateaus. If we further take a derivative, then the subband structure of the waveguide is revealed, and it was also theoretically verified. And like I previously mentioned, the most interesting aspect about these electron waveguides is the observance of paired electron states till fields as high as 9 Tesla. So now we wanted to study the electron pairing along with the Hall properties, and we also wanted to have control over the domain properties like I previously mentioned. So whenever we think about the Hall properties, the first thing which would come to our mind is a cross. So here we have a nanoscale cross which is 1 by 1 micrometer in dimension, and surrounded by 4 highly transparent barriers so that we can tune its chemical potential with the help of a side gate. And what is particularly nice about these nanocrosses is that we can define the X, Y, and Z domains at the interface because of the nanocross geometry and the lithography process, and we can simultaneously study the longitudinal properties and the Hall properties. So we write these nanocrosses using CAFM lithography, and we take low temperature magnetotransport measurements. So here we have 2 particular configurations across the nanocross, which I call the horizontal and the vertical configuration. And what we observed was an inhomogeneous energy landscape across the nanocross. So if you look at the 2 states and their subband structure, the vertical configuration is far more conducting than the horizontal configuration. Also, I would like to point out that this particular configuration is the corresponding Hall configuration for the horizontal case. So the Hall configuration is always conducting for the corresponding horizontal configuration. One of the most interesting aspect is again the observance of electron pairing without superconductivity. So if you see for the horizontal configuration, somewhere between 4 to 6 Tesla, the electrons goes from a paired state to the unpaired state. So I would like to further concentrate on this particular configuration. So here I have drawn the points along this curve in order to clearly show the depairing mechanism. And if you look at this particular curve over here, we can clearly see that the depairing takes place at around 5 Tesla. Now, if we look at the corresponding Hall configuration, then we do observe a nonlinear Hall effect, and interestingly, the non-linearity also takes place around 5 Tesla. So the pairing mechanism and the anomalous Hall effect across the nanocross definitely seems to be directly correlated. So our next goal was to understand that what can be the correlation link between the two. So here I have a very simple picture where I am trying to portray the Lifshitz transition, which has been widely attributed to the nonlinear Hall effect. So we are keeping the field to be 0, and we consider the chemical potential to be below the Lifshitz transition. So under such circumstances, the chemical potential is much lower than the pairing potential. And so all the electrons would be in the paired state, which would be the dxy, the spin singlet state of the dxy band. But now, following the traditional Lifshitz approach, if we increase the chemical potential such that it is higher than the pairing potential, then the electrons can exist in both paired and unpaired states. But this is this is the approach which has been followed till date, but there is another picture which can be actually added to it. So now what we do is that we keep the chemical potential to be below the Lifshitz transition, but we increase the field. So in this picture, the spin polarized states actually shift in energy, and even though we are below the Lifshitz transition point, the electrons can still exist in both paired and unpaired state. And in order to elaborate this picture more, I would like to show a simulation. So this point is the traditional Lifshitz transition point at B is equals to 0. So if we are at 0 magnetic field, the electrons will start going from the paired to unpaired state at this particular point. But now if we apply magnetic field, then you can notice along these dashed gray lines that this point at which the transition takes place can actually shift. So if we consider at this particular magnetic field that somewhere around here, the electrons will start going from the paired to the unpaired state. So anywhere inside this triangle, the electrons exist only in the paired states, and anywhere outside this triangle, the electrons will be in both paired and unpaired state depending on our magnetic field. So if we consider this case over here, the purple is the paired state and the red is the spin polarized down unpaired state. And If we consider this particular case over here, again we have the paired state, and the blue is the unpaired electron in the spin polarized up state. And these cases over here are the intermediate cases where we have both paired spin polarized up and down and paired states. So now I would like to also introduce some concepts on how the domains can come into picture. So like I said, below this magnetic field and below the Lifshitz transition, the electrons can only exist in the paired states, and we believe that this would be dominated by the z domains, so the electrons will be confined to the z domains, which is dominated by the dxy band. However, now if we still keep our chemical potential to be below the Lifshitz transition, but we increase the field above this depairing field, what happens is that now the electrons, according to this picture, can exist in both paired and unpaired state. And the electrons now gain sufficient energy to actually cross the z domains and go to the x and y domains, which are dominated by the dxz, dyz bands. And this transition of the electrons from the paired to the unpaired states, and possibly from the z domains to the x and y domains, can lead to the anomalous Hall effect. So in summary, we write 1D nanocrosses at the LO-STO interface using CAFM lithography, and we observe a direct correlation between the pairing mechanism and the Hall properties at the interface. We believe that the ferroelastic domains in STO can be a possible correlating link, and that the transition of electrons from the paired to the unpaired states is accompanied by a real space transition of electrons from the z domains to the x and y domains, which leads to this anomalous Hall effect. With this, I would like to thank you for your attention, and there will be many other talks being posted by my group. Thank you.